Visualizing parent functions. It's important to be able to visualize mentally the graphical image of a function when given an algebraic description. So let's practice accurately graphing our parent functions. So the constant parent is going to be f of x equals some constant. So that general equation is f of x equals b, and b is that y-intercept. So here the y-intercept is 0, -2. So we plot that y-intercept, and then we draw a horizontal line. And there is our constant function. Next, we have our parent linear function, f of x equals x. So this goes through the origin, and we have a slope of +1. So next we have the absolute value parent function. That's f of x equals the absolute value of x, and this is actually a piecewise function made up of two linear functions that meet at a vertex. For the parent, the vertex is at the origin, and then the slopes here are a +1 and then -1. Notice that we have a V shape. Okay, our next parent function is the quadratic function, f of x equals x squared. So this has a parabola shape or a U shape. The vertex is at the origin, and we need to accurately graph this. So I recommend creating a table of values. So every input is going to get squared to give us that output. So when our input is 1, our output is 1. When our input is -1, the output is 1. Notice we have that reflection over the y-axis. 2, output 4, input -2, output 4. So then, using our table of values, we can plot the points, and we know it's that parabola shape, so we can draw that shape. Next parent function is the square root. We can only take square roots of positive numbers to get real outputs. So therefore, we start at the origin. And then let's create a table of values where our inputs are perfect squares. So when our input is 1, our output is 1. Input is 4, output is 2. Input is 9, output is 3. So it has this kind of curved shape to it. We know square root is like this. Okay, our next parent function is cubic. f of x equals x cubed. All inputs are going to be cubed. So let's create that table of values again. Our cubic graph goes through the origin. And then whenever we cube 1, we get an output of 1. When we cube -1, we get an output of 1. Cube 2, output of 8. Cube -2, output of -8. So it creates this shape. All right, our next parent function, exponential. You worked with exponential functions a lot in Algebra 1. You might have been familiar with a times b to the x, or maybe just b to the x. Well, here, our parent exponential, f of x equals e to the x. E is a famous constant, Euler's constant. It's approximately 2.718. It's a famous irrational number. And this exponential parent is one of our parent functions that does not go through the origin, because anything raised to the power of 0 equals 1. Also, we cannot raise anything to a power to equal 0. So this function gets as close as it can without ever reaching the x-axis. So I'll show you what that looks like. So we're going to have a point at 0, 1. Again, anything raised to the power of 0 equals 1. And then on the left side of that point, we're as close to the x-axis as we can, but we don't touch it. And then we have a steep curve. Might not have been steep enough. Hold on. So the important features are this boundary line, or the proper name is an asymptote. It's right there at the x-axis. We have that steep curve, and then we have the point 0, 1. All right, logarithmic. So here we have f of x equals ln of x. Again, that's L n of x. That just stands for natural log. Logarithmic function is actually the inverse of an exponential function, so it has opposite features. So whereas an exponential function doesn't touch the x-axis, logarithmic doesn't touch the y-axis. Whereas exponential had that point at 0, 1, here we have the point 1, 0. And then it doesn't touch the y-axis, and then it actually curves quickly this way. All right, here we have the greatest integer function, or the step function. F of x equals, and then those brackets around x. This is a rounding function. It rounds everything down to the nearest whole number. So for example, 1.25, that would round down to 1. 0.999999999, maybe forever, that rounds down to 0. So anything between 0 and 1 has the same value of 0 until we get to 1. So we have that point at the origin, and then all the way up until 1. And the second we get to 1, it's not included here, but instead it's included here. And that continues because of that rounded down aspect of it. Same this way. And then it continues forever. One way to check this, you should be able to draw a parent linear function through these points. Notice how right there, our closed points forms a linear function. The reason this is oftentimes called step function is it looks like steps. Just make sure you know where your closed and open circles go. Here we have our reciprocal function, f of x equals 1 over x. Over x. This is a very important function for modeling. So for the reciprocal function, we're going to have asymptotes at x equals 0 and y equals 0. Okay? So you can create a table of values to help you. So when x is 1, 1 divided by 1 is 1. When x is negative 1, 1 divided by negative 1 is negative 1. And then we have 2, 1/2, -2, -1/2. And so what's happening here is we're getting closer to the x-axis without actually touching it. So our reciprocal function looks something like here. So our reciprocal function looks something like this. Having a tough time drawing this on my iPad. My apologies. And then over here like this. Lastly, we have our sinusoidal graph, or our sine graph. F of x equals sine of x. You probably remember this from geometry. You learned about the sine ratio. Well, the function is very important for Algebra 2 for when we're modeling cyclical data. So you don't have to be able to graph this, but you need to be aware of the shape and how we're going to have restrictions here of the range. So those are all the parent functions you need to be familiar with, and also you need to have the ability to graph them accurately.